Now is okay. I don't know.
Yeah, yes, sir. Now it's opening. You just you full view screen, sir. Full view. Now it is visible, sir.
New share. No. This advances and this. Can I share or no?
Now it has been gone, sir. Your screen has been gone now, sir.
Now is okay, maybe?
Yeah. Just a second, sir. Yeah, it was open, sir. You just give the full
Okay,
view, sir.
okay.
Full view, it is visible to all, sir.
Yeah, please. Now, can you see that the slide?
Yes, sir.
Okay, just 1 minute. Now is okay?
Yes, sir. Fine, sir. Fine.
Sorry, actually, just for interruption. First of all, thank you, actually, Professor Priya Murugesan, for your kind introduction and to introduce me with the audience, all distinguished research scholars, participants, ladies and gentlemen. Very good morning. Thank you again to Shabita Engineering College for inviting me to give a webinar international lecture. The title of my talk is Nanostructured Metal Oxides Thin Films for Sensor Application. We know this is very important and interesting subject to us, as the nanostructured metal oxides, thin films, and sensors are playing very vital role in our everyday life due to their importance in modern technology. So before deliver my presentation, let me introduce first my institution, where I am from. Bangladesh University of Engineering and Technology is the oldest institution in Bangladesh. It is about 145 years old, located in the capital of Bangladesh. Its first journey started in 1876 as a Dhaka service school, then became the Arsenal School of Engineering in 1908, and then Arsenal Engineering College in 1947, and finally full-fledged university started on June 1962 as Bangladesh University of Engineering and Technology. We have 5 faculties and 18 departments. So Faculty of Electrical and Electronic Engineering, Faculty of Engineering, Faculty of Civil Engineering, Faculty of Mechanical Engineering, Architecture and Regional Planning. So there are all these engineering departments: electrical, computer science, chemical, material, metallurgical engineering, and all basic science, physics, chemistry, mathematics, petroleum and mineral engineering, resource, glass and ceramics, civil engineering, water resource, mechanical engineering, naval architecture, industrial production engineering, biomedical engineering, architecture, urban regional planning, and humanities. And there are 6 institutes and 6 research centers. We are about 600 faculty staff and 7,500 students in the campus. So I will show some slides, academic and administrative buildings in the campus. This is our old academic building. This is a civil engineering building. This is the mechanical engineering department. This is electrical and computer engineering department. And this is the architecture and regional planning department. And there are some more academic and administrative buildings in the campus. So these are the all buildings, the few buildings and institutions actually I have shown here. This is the country overview of Bangladesh. You know that is a neighbor country to India in all sides except the Bay of Bengal. So this is the national monument. This is our assembly house. And we have the long, the river bridge over the Jamuna. We have the longest sea beach and convention hall for international conference and meetings. And this is the city around the campus actually. and this is the bridge also and the lake. Here, this is the Department of Physics, University of Dhaka. We are very much familiar with the Higgs boson and the boson particle. These particles are indistinguishable, and this particle was discovered by Professor Satyendranath Bose. He was a teacher of this Department of Physics. During his teaching in the department to the postgraduate students, he discovered the indistinguishable particle that is known as the boson. Is having the whole number of the spin number is complete number. And I feel proud to be a postgraduate student of this department. This is the physics department of Dhaka University. And this photograph of Professor Satyendranath Bose. He was teaching the department since 2021 to 1921 to 1945. And the key words actually about my presentation, I will come to my main topic, the metal oxides, nanostructured, metal oxides, thin films, doping, deposition technique, and sensing properties. Metal oxides are abundantly available in the earth. There are two groups, mainly the transition metal oxides and non-transition metal oxides. Again, the non-transition metal oxide is divided into two groups, the pre-transition metal oxides and post-transition metal oxides. These are belongs to aluminum oxide, magnesium oxide, zinc oxide, tin oxides, and nickel oxides, ferric oxides, chromium oxides. So these are transition metal. Here again, there are more metal oxides like the alkaline earth metal oxides and the poor metal oxides, the rare earth metal oxides. So these are the classification of the metal oxides material, the overview. Why this is important actually, these are the transition metal oxides, because the transition metal oxides are called the D metal or the D shell orbit actually here. So this material can change the oxidation number, can change the coordination number, and also make the colored compound. And because of in the D shell, they have the unoccupied or unfilled actually electrons. Here we see that these are the shell, electron shell, and these are the soft shells here. So these the transition metals is having the in the D shell is the odd or even number of the electron configuration are most suitable for the gas sensor applications. Here is the zinc oxide, tin oxide, titanium oxide, dioxide, and tungsten oxide, vanadium oxide. So these are the series of the transition metal we can show. Here, if you look at this actually, this chart here, copper, cobalt, manganese, and chromium, the D shell contains the odd number of the electron configuration, 9, 7, 5, 3. So in the periodic table here, you see that the chromium, the cobalt, the copper, these materials have the odd number of the electrons in the. So these odd number of electrons metal behaves as also insulator sometimes. So these are the mainly the D shell is fully not fully occupied, and these are the characteristics of these the transition metal oxides. And these are the beauty to change the chemical bonding, chemical reactivity, the oxidation state and oxidation number and coordination number. So because of this speciality, we always prefer the transition metal oxides. And we also look for that the transparent metal oxides here. Because why the metal oxides? This metal oxide surface is electron rich. They can interact with the target molecules and to change the chemical properties. So metal oxides are well-known material for sensors and biosensors application due to the low cost, high sensitivity and simplicity, and also the stability. And nowadays, the most advances in the nanotechnology research, the people are trying to reduce the particle to nanoscale because of the more surface area and induce the new effect due to the quantum confinement, such as the bandgap widening at room temperature. Also, we have the photoluminescence properties. So these are the actually the specialty of these the metal oxides films. And also these metal oxides, uh, they can produce the all microelectronic devices to create the Schottky contacts, metal oxides, resistive random access memories in electrochemistry for contact electrodes. So these are the metal oxides interfaces are used in these families for the microelectronics devices. So our main approach in depositing the metal nanoparticles on the surface of oxide, these metal oxides actually were given more attention just after the discovery of the MOSFET in 1960. Because of these metal oxides have the larger band gap, highly transparent in the visible region, capability of absorbing the ultraviolet light, high conductivity and poor mobility, producing the electron hole pairs, nice electrochemical responses, good mechanical properties and thermal stability. So these are the special properties of these metal oxides. Here, the some devices I will show the application of metal oxides. Thin films, as a transparent metal oxides, thin films have applications in optoelectronic devices, gas sensors, humidity sensors, and microwave devices, supercapacitors, lithium ion batteries, high density recording media, solar cells, solar filters, transistors, organic light emitting devices, optical lenses, and optical windows. Here, this is the concept of nanoparticle nanomaterials was given by the Richard Feynman, the US physicist and the Nobel Prize winner. And when he was talking to the American Physical Society annual meeting in 1959, he talked about there is plenty of room at the bottom. And in his presentation, Feynman gave some ideas about creating the nanoscale machines to manipulate, to control, and image matter at the atomic scales. So then people are searching to produce the nanomaterials. And there are two approaches, actually, two different approaches to fabricate the nanomaterials. One is the top to down process, and another is bottom to up process. For any from any bulk material, we can cut the materials into from bulk to into small pieces. So this is process is known as the top down process. Again, from bottom to up is the building of these the blocks, like the atom by atom, molecule by molecule, or cluster by clusters. We can assemble these all building block materials like the atoms or molecules or radicals or ions to form that the bulk material from nano material to the bulk material, or from atomic level to the bulk material size. Nanostructures, the important is actually these nanostructures refer to material or structures at least the dimension in between the 1 to 100 nanometer. Nanomaterials have several advantages over the bulk materials because of huge surface to volume ratio, high porosity, completely different physicochemical properties, and they are much more stronger, lighter, more durable, more reactive, more sieve-like, and better electrical conductors, among many other traits. And there are different types of the nanomaterials, nanostructures, and based on these, the crystallographic orientations, morphologies, and characteristics, and unit cell structures. So we can classify the nanomaterials in the form of the nanowires, nanofibers, nanotubes, nanobelts, nanofluid, quantum dots, nanosheet, nanocomposite, nanoparticle, and nano ribbons. So these depends on that the crystallographic orientations, morphologies, and arrangement of atoms. Here, the properties of nanomaterials you see, when you reduce the size of the material from bulk to the nanomaterial, then as the size is reduces, then increases the surface area and increases the antibacterial properties, is able to increase the hardness, electron band gap, electric properties, magnetic properties. So all of these physical, chemical, structural, optical, electrical, magnetic properties will be increased due to size effect. Here, why we need actually sensor materials? Sensor, it is an electrical, mechanical chemical device that detects and responds to some type of input from the physical environment. So the physical environment means we are meeting always with the light, heat, motion, moisture, pressure, and any one of the great number of other environmental phenomena that can sense by the device and can give the actually in the instrument give you the information about the conversion of these the input signal into the output. So a sensor measures a physical quantity and converts it into a signal which can be read by an instrument. So that's why we need that actually the sensors in all. This is also called the intelligent environment to detect the information from the environment. Here, you see here, the spray pyrolysis systems, there are many other techniques are used to fabricate the nanomaterials, sol gel method, and the low temperature, that is the call, the spray pyrolysis temperature is all, spray pyrolysis technique is also useful for produce the nanomaterials. And here I will show this, the technique which we have fabricated in our lab, and I will say this is very simple. This is a continuous process, low cost setup, and a large scale area deposition, easy to control, easy to fabricate, and overall we don't need any vacuum systems. So here, this process is actually, we have to optimize some conditions for before depositions. The conditions is parameters like the deposition temperature is the main important part, concentration of the salts, doping percentage of transition metal or any metal, spray rate, carrier air pressure, nozzle to substrate distance. So these are the all important growth parameters we need to optimize for optimum condition of the film or for the quality of the film. If we want to grow, then we have to compromise fast. Second is actually, you see here, this is the setup of the spray pyrolysis systems. Here, we need the air carrier gas. This is the compressor we use to push the air to the channel, and this is the nozzle, and this is the aqueous solutions. By siphonic pressure, it comes at the end of the needle, and this is the nozzle, and by the air pressure, all these aqueous solutions are coming up into the form of the small the water droplet, and it falls on the surface. This is the called the substrate, and there is a hot plate is there, and it is maintained actually to make the bond thermal stimulation and formation of the crystals actually is depends on this the temperature. So here are two processes, mainly the pyrolysis and hydrolysis process. First of all, we have to prepare the ionic solutions, and this preparation of solution of salts is called the hydrolysis process, and mostly we use the water, plain water, to dissolve the salts, and then the process is called the pyrolysis, the formation of the thin films on the hot plate on the substrate. And here we can use any substrate. The temperature, we don't need the high quality substrate, high quality the chemicals. So very low grade chemicals also we can use, and by filtration we can remove the impurities. And this process here we use the plain glass substrate. And this temperature is controlled by the variac, and we can control the temperature and measure by optical this the device, the pyrometer, or as well we can measure it by the thermocouple. Here, you see there are the four forces actually involved for formation of this the droplet and for the formation of the nucleation. Here is the first is the gravitational force. This force is equal to, this is the spherical shape. That's why 4 pi by 3. And due to the gravity, the water molecules are falling down from the nozzle to the hot plate. And electrical force is responsible for making the bonds. And here the F equal to Q E, this is the electrical field. And thermophoric force actually, thermophoretic force is related to transportation of the particle away from the high temperature to the low temperature. Is always tendency to move the particle from in the direction of the low temperature. So this is the thermophoretic force is coming up, and again the Stokes force, that is the friction in between the air molecules and the droplet. The Stokes force is a factor for the particle's velocity and size. So these four forces are involved in the formation of the thin films over the substrate at a hot plate. Here, after the deposition, we need to characterize the sample. And we characterized the structural characterization by Oxide and the bonding characterization so by the Raman spectroscopy, field emission, scanning electrons microscopy is for the surface morphology, elemental composition by EDX and dispersive X-ray, and UV visible near infrared spectroscopy for optical calculating the band gap, and 4-point probe method for electrical, Hall effect measurement, and hysteresis for magnetic studies, BSM. We employed all these techniques to characterize our as deposited samples. Here, some structural parameters we need to use these to calculate the crystallite size, strain, dislocation density, microstress, structure coefficient, lattice parameters. So these are all these equations, standard equation. We have also developed this the physio fringe method, multiple beam interference ferrometry. Here we have to calculate the step height and fringe spacing using that the sodium lamp. So using these equations, we can calculate the thickness of the film. This is the simple Newton's ring experiment, same type actually. So using this physio fringe method, we calculated the thickness of the films, and it is about more accurately we can calculate actually maybe plus minus 5% or 10% error. But even then we can calculate if we take the several readings and take the average values. Next, you see, now I will show some slides about our thin films depositions. Mostly these all these films were deposited by my postgraduate research students, some PhD students, MPhil students, MSc students. They did it all these the thin film deposition and characterizations. First of all, the zinc oxide, I will show tin oxide, iron oxide, titanium dioxide, cobalt oxide, manganese oxide. So these are the all oxide materials. I will show the results actually. First of all, the zinc oxides, the thin films. Here, zinc oxide thin films, here you see this is the Oxide structures and hexagonal structures. And second, this we use actually the zinc acetate solutions to prepare the our thin films, zinc oxides, and prepared at in water solutions. We maintained the solutions is 0.1 molar concentrations, and these 10 to 30 minutes is the deposition time, and nozzle to substrate distance is about 25 centimeter for these purposes. And you see here the carbon dioxides and methane and steams, they are all coming up in the form of the volatile product, but residue remains on the substrate in the form of the zinc oxides. Here, these are the substrates. You can see the excess of the zinc, it gives the deep brown color. So on the glass substrates, we have deposited the zinc oxides here. Then you see, this is the zinc oxides nanofiber. You see, the zinc oxide is very promising material for versatile applications. Here, the zinc oxides, we got the nanofiber structures, and we deposited it around 250 to 300 degrees centigrade, and then annealed also 400 and 500 for good compact and homogeneous structures. Here you see, initially that was at the 300, then this is the 400, and again fiber is becoming more prominent, and finally this shape you see that at 500 more clear. So we observed after annealing, the fibers become clear and narrower. The average diameter of the fiber is around 220 nanometer. We calculated the actually grain size here. You see, The grain size is the small crystallite size, that is also called the grain size. Here you see that after annealing, at starting from the 300 and to 600, so the grain size is reduced to 20 nanometer here. This is the nanometer scale. And optical transparency is actually is reduced here because of the annealing. We have seen that the deep colored films produced at the high temperature because of the excess of zinc, and then the transparency is reduced here. Again, the band gap we calculated, and here see that the band gap is 3.4 electron volt to 3.31 electron volt at a high temperature. The band gap is reducing here. So this is the, and related to the refractive index is also, we can see the quality of the optical properties of the film by calculating the refractive index also. Second, this actually was published in Crystal Research Technology. It has got the citations is about 160. So it's a very good article. Then we said in our paper that we first observed the nanofiber structures from the simple technique, the spray pyrolysis technique using the zinc acetate solutions. Second, I'll talk about the cadmium doped zinc oxides. Mainly, you see here that this is the fiber structures at the pure form, the pure zinc oxides. Again, at the low concentration, still the fibers exist there, but after higher concentration of the cadmium, that is broken. These fibers are broken and ultimately form the small grains and porous structures, and ultimately at 8% the cadmium, we got this small particle. And this is also, we communicated the optoelectronics and advanced materials rapid communications in very old paper, but is well cited also this article, the change of this fiber into the nanoparticle size. Again, we use the nickel, that we change the, actually this you see at the 5% nickel doped, that the grain size is reduced to here 11 nanometer. So that is for tuning the band gap, for tuning the optical properties, that we did it using the transition metal like the nickel or cadmium or copper or iron. So to change the properties, actually, this is our main objective, to reduce and how to grow the nanostructures material from the transitional metals. So that paper is also we published in a Journal of Physical Chemistry in 2013. This band gap tuning of zinc oxide through nickel doping by a spray pyrolysis technique. This is the copper doped tin oxides here. This is the copper doped tin oxide you see here. This is the pure the tin oxides material on the glass substrates, and here when we doped that 2% copper, then we see that the small the hole and the porous structures form. So this is because of the interaction of the copper into the tin oxides. And then again we see 4% is the copper doped tin oxides, and this is the 5% copper doped tin oxides. So the tin oxides is very important material actually for the gas sensors, especially the hydrogen gas sensors we tested is also these tin oxides, and this is a unique material. And now the people are searching the other oxide materials like the cobalt oxides or manganese oxides, but still the zinc or tin oxide is more common for the gas sensors applications. Here we have seen that again, the band gap and the doping for this 4% here, the band gap is 3.5, and in between this 3.75 to 3.85. So this is a direct band gap. Here we got it at the minimum for the 4% because of that the small crystallites form at the 4%. So that paper is also published in the Journal of Optoelectronics and Advanced Materials here, and we calculated actually the direct band gap here. What is happening actually in the band gap? you see, when you doped some doping element gives the extra electron, and that due to this excess of electron is shifted to the Fermi energy level from valence band to the conduction band. So this is the mechanism of having that the small crystallite size, optical band gap value of copper doped tin oxides as a function of copper doping concentrations. So these are the main reason for shifting of the Fermi energy level due to the transfer of electrons from valence band to the conduction band due to the excess of this the doping element. Here you see here, this is the particle size, and this particle consists of the small crystallite size. Is always whatever we do using that the XRD, we calculate the crystallite size, or we can say in general the grain size. So these are the small is the grain, and as a whole, with the lots of the grain or crystallite size gives the particle size. So when we use the XRD, actually you are calculating the crystallite size, not the particle size, just for understanding. Here, what is happening actually, you see here the porous layer of the grains, compact layer of the grains. So compact, if you have the more compact, then the less gas can go inside the material. But if it is the porous structures, and so the gas molecule can entrapped into the space in between the grains. So because of that absorptions and the porous structures, these materials are suitable for the gas absorptions material. So this is the schematic mechanism for absorptions of gas within the small grains or particles or porous or nanostructures materials here. This is the same compact here. Here you see here, what is happening actually the resistance is developed here. And what is the reason actually see here? These are all the three grains. And outer size is the absorbed oxygens. When these two grains come in contact, so the neighbor, these free oxygen and neighbor oxygens, so back to back oxygens, they try to combine the repulsive force, and they produce the higher resistance at this layer actually. So, and they produce the depletion layer. And depletion, how? This is the size of the particle is the D. And normal depletion layer or the Debye layer, we say this is the L. L means in between these, the neighbor to electron, charge electron. So this is here is the back to back. When they come, there is a repulsive force comes and it produces the resistivity. And due to this, it gives rise to high resistance values at these the contact points. And normally the Debye layer or depletion layer is around 100 nanometer and much smaller than the grain size. This is the grain size is maybe about the 500 nanometer, and the depletion layer is less than the 100 nanometer. So because of this, the resistance is developed due to the come in contact the all charge to the neighbor, the grains, and this back-to-back electron charge form the formidable barrier for electron to cross. So here, this intergranular contact resistance comes from the interaction of these charge particles. The height of the energy barrier, this is called the height of the energy barrier, is reduced here again, then ultimately it will go to that balance to the conduction band. There's electric current flows, and the cause of the resistance is because of the charge particle mainly. Here, these iron oxides, recently one of my students actually, she completed this PhD and she did the iron oxide in details for his PhD thesis. Here you see that the iron oxides, this is the pure form, pure iron oxides, and only we change the temperature, deposition temperature, and to see what is the effect of the temperature on the formation of the nanostructures material. Here you see the iron oxides, ferric oxides, is it the substrate temperature is starting from 350 to 400, 450 and 500 degree Celsius, and this is the distribution of the particle size here, and mainly the growth mechanism is different at different substrate temperatures, which affects the surface morphology of the material. So here you're starting, see, with the increasing the substrate temperature, what will form actually from droplet to precipitate, precipitate to vapor form, vapor to the solid particle, and ultimately is a good addition on the substrate. So always that there is the influence of temperature on the substrate. So if we increase the temperature, definitely we'll find some droplet and more compact and more the binding and strong formation and good the films we can produce just changing the temperature here. So this is again the 450 temperature annealed. After annealing, there is the effect of annealing temperature on the film's morphology. Here you see here annealed at the 450 temperatures. 450 is the annealing temperatures, and we have see that the distribution of the particle size here. So we calculated actually the elemental compositions from the EDX study here. So these are the EDX spectrum. It gives you the composition of the element, and mainly the composition of the element is iron and oxygen. So we eliminated the other impurities like the glass substrates. If we use, we have the calcium, magnesium, or other impurities on the glass substrates, but that we remove that the impurities. So the main stoichiometric of this film is the iron and oxygen. So these are the stoichiometric conditions of atomic percentage of iron and oxygen. So here you see. Next, you see that the topographical analysis, if you want to see that the three-dimensional views of the formation of the films, then you need to study the actually this AFM study. So AFM will give you the more information about the three-dimensional image. Here is the iron oxides and at different temperatures, and we have seen here is the average roughness and RMS roughness is calculated here. So average roughness and RF roughness as you see here, and when you increase the temperature, that automatically the average roughness is increased and RMS values is also will be increased here, and this is the as deposited, but for the annealed sample, you have the better. You see that the main average roughness is 7.80 and 500 is the 39. Again, the RMS roughness is here 49. Because of annealed samples, you have the better. So from other earlier reports, actually, it was found that the gas sensing material work efficiently if the average roughness can be kept less than the 50 nanometer. So the report is there. If we can tune the particle sizes less than the 50 nanometer, that is suitable for the gas sensing purpose. And here also we have seen that the average, the grain size and the particle size, grain size is here less than the 50. So we can conclude that this product could be suitable for the gas sensing purposes. Here again, the ferric oxide is we have done. This is the actually the less crystalline, is not sharp the reflection peak from the XRD we have. So we say this is the less crystalline, but it can be improved after annealing. So here the presence of unreacted amorphous agglomerates, because of this the unagglomerated particle and not completely that is oxides form. There are some remaining few unreactive material, and because of that we have the less the crystalline structures here. Again, this is the equations already I mentioned my previous lectures. Here here you see that the structural parameters, the average diameter crystallite size here is 300 degrees 64, and ultimately at 500 we are able to reduce the crystallite size is 36. So it is confirmed that the annealing temperature is playing an important role for reducing the nanostructures material. So here we also calculated the dislocation density and strain of these all the as deposited and annealed samples. So decrease of the grain size, actually diameter of the grain size with the substrate temperature may be attributed to the formation of the smaller nanoparticles agglomerates as the effect of change of the growth mechanism as found from the field emission scanning electron microscope. So SEM studies, we have seen that the agglomeration is less and is more compact, and the particle size is also reduced. So increasing should be is the strain and dislocation indicates the increase of deformation in the size of the particle and dislocations in the whole structures automatically. Here, these are the structures of this after annealing. No corresponding other peaks are found, mainly the very sharp peak. It means that it is the pure face, and no other faces are here, only the pure faces. So XRD peaks are appearing, and is appearing often irregular manner as an effect of rearrangement in crystalline orientation due to the annealing effect. So these are the XRD patterns for the as deposited sample, for the annealed sample. So that improvement of the crystallite size that we have got after annealing. So these are the size actually again, these 43, 44. Here is you see that 45 annealed. After annealing, the diameter of these, the grain size decreases in the film here in between the 300 to 400. But again, due to the removal of unreacted particle and structures. But again, the films at 500 to have the distinct particles agglomerate. During annealing, the particle got enough excitation to move towards the grain boundaries, and D is increased because of that high temperature. So this is not only that increasing temperature only give you the favorable conditions or favorable size. You have to optimize and you have to tune that. Depends on that the material to material. Second, the optical transmittance is also, you see here, reduced after increasing that the temperature, and increase of transparency with in the range of 300 to 450 may be attributed to the decrease of that optical properties is related to the size of the grain is always. So reduction of transmittance at around 500 may occur due to the high surface roughness of the film, despite having the less degree of the grain size, diameter of the grain size here. So these are optical, and these are the absorption coefficient, tau formula, extension coefficient, so that we can calculate from the, here you see this is the direct and indirect bandgap mainly. Actually, these materials mainly, if you have the highest the electron saturation and the minimum electron from the conduction band are lying on the same wave number, the momentum is the same. So then you have the K, so wave vector is the same. So then you can say this is the transition, is the direct transitions. If that the K, the number is the change, so the momentum, due to that momentum is different because of that the interaction of phonon or electron or phonon electron interaction. So that changes the band gap actually. So this is the indirect band gap. So here the same value of the K, the momentum on the same line, so is the direct band gap, satisfy the condition of the energy and momentum conservation. But indirect band gap that have the maximum the balance and minimum the conduction band do not occur on the same wave number, or this is the quantum state, momentum state. So that give you the indirect band gap. So you can calculate when the absorption coefficient is a square and the versus axis is the h nu. So you can directly calculate the direct band gap when this is the absorption coefficient root and the energy. So these direct extrapolation of this straight line to the these absorptions line. So you can calculate on the x-axis the band gap. So this is the direct and this is the indirect band gap. Here, this is the four probe method. We need to use this four probe method for calculating that the resistivity here. This is not the metallic, this is the semiconductor material. And so this is suitable for calculating that the band energy gap using that four probe method. So here you see, this is the step, this is the S is and V, the voltage and current, and S is the separation between the two these electrodes. So easily we can calculate the resistivity and activation energy using these equations. We can vary the temperature in the closed systems inside these the four probe systems is there. So we can calculate and we can use this the four probe method. And that is also actually developed in our department. Our students have developed this electrical transportation properties. That this is a very important. We need to test actually the resistivity. Unless we determine the resistivity, we cannot say this material is completely suitable for the gas absorptions or other optoelectronic properties. So this resistivity, because of that the carrier concentration depends on that carrier concentration. So resistivity here you see on a particular temperature or on a particular concentration of doping level, they reduce the minimum resistivity. So here you see that at 400 degree centigrade, we have the minimum resistivity, carrier concentration is high. Again, here is the 400 is you see here after annealing, that temperature is also, there is a co-relevant actually with the as deposited and the annealed samples. So we have measured the resistivity using this four probe method. Third, actually, aluminum doped iron oxides also. That is all the part of my students that PhD work. She did it. This is the pure aluminum oxides here deposited at 300. So these are the small the grains we have seen here. And next, you see that aluminum is doped with the iron. This is the pure form. 2 atomic percent, 4 atomic percent, 6 and 8 atomic percents here. So we see there is a variation of the surface morphology with the doping level of the aluminum on the iron oxides. So this is a very cheap material. That's why we selected this iron oxides, whether these iron oxides could be suitable for the gas sensing purpose. Here we did the XRD. Here is this aluminum doped, different variation of this aluminum doped the thin films. The XRD pattern is there. And then next they calculated this the grain size. Here you see that the 4 aluminum percent is low concentration is always a suitable for actually here. See, there is a 56 nanometer size, and here is the 2% is also 48. And again, it started the diameter is increasing here. So if you see the dislocation and strain and porosity is also this part we calculated here. So this aluminum doped iron oxides here, you see this transparency is increased here with the aluminum doping. And a small variation is there, 6% there, but again 8% is lower. So these results we published, communicated in the Semiconductor Science and Technology, this 2019. That was the part of his PhD work. Again, this is the summary of the aluminum doped iron oxides thin films actually. Here, the homogeneous surface morphology, regulated topological features. We have the better crystallinity, high transparency, and reactive index. Refractive index we calculated, tunable and wide bandgap, less electrical resistivity. So this may be suitable for the fabrication of the optoelectronic device out of his surface morphology and electrical characteristics and the surface properties. We can say this is the suitability of this material. Next is the zinc doped the titanium oxides. We are giving all these the material transition metal oxides mainly for application point of view and to produce the nanoparticle, nano size. And you see here, these are the titanium dioxide and doped with the zinc here. This is the pure form, and then started to change the surface morphology. And here, these are 2%, 4%, 6%, 8% zinc doped. And we have seen that there is a change of the surface morphology here. So this change will give you the better information. Here is these are actually, there are many phases. Rotile anaphase, brochite phase is there, titanium dioxides. Here mainly we got from the XRD, this is the anatase phase and strongly oriented along the 101 plane. So we can say this is the anatase phase. with increasing the zinc, grains become compact, denser, and agglomeration. It is about the 6% the zinc doped gives you the better agglomeration and denser and compact. And these are the properties you have seen here. And you see that the zinc concentration 0 to 4.6 here is 2% and 3%, 6%, 8% is increasing here, the direct band gap material. Although this, what's the features of these zinc doped titanium dioxides? SEM images show the uniform distribution of grains over the entire surface of the film. XRD results show the annealed films are crystalline in nature. Obviously, it should be, and with the preferred orientation along 101 plan. Transmittance of doped films increases up to 90% for 4 atomic percent zinc concentration. Band gap increases with the doping concentrations and varies in between 3.5 electron volt to 3.75. Resistivity decreases with increasing temperature for both the undoped and doped films, and the value is varied in the order of 10 to the power 1 to 10 to the power 2 order ohm meter. And we can conclude that these tin doped, zinc doped the tin oxides could be suitable for fabrication because of that nano size and nanoparticles and agglomerations. Again, aluminum doped tin oxides. These are the porosity here, the small is very clear. The aluminum doped tin oxides, if we do it here, see, this is the small hole, and the features is like the sponge shape. So this hole can absorb the uptake all the gas molecules. So this type of formation is possible when we slowly doped and low concentration the doping element of aluminum, because these are not very costly compound. This is very inexpensive. So we can use, we have used this aluminum as a dopant to titanium dioxides, and we have got very good features. And it seems that these are suitable for the gas absorptions and sensors purpose. Here is also atomic force microscopy we have done here. These aluminum doped titanium dioxides, and next I will show these copper doped cobalt oxides here. That is also part of this the PhD work. One of my students, she did this work, and this cobalt oxide. Why this is a cobalt oxide actually? Cobalt oxide is a promising material. In the first lectures, I have mentioned that because of this cobalt, these are all the suitable material for recent studies. They select these the cobalt oxide, tungsten oxides are suitable for the gas sensing purpose, and especially for the biological the sensors like the glucose sensors. These are suitable. Here, the cobalt oxides is the p-type semiconductor and is the most promising transition metal oxides because of excellent chemical and thermal stability, low toxicity, mechanical hardness, high electrical conductivity, and it is used as a sensor in non-invasive health monitoring applications like drug delivery, glucose sensors, cancer cells detections, so and so. So here, these are the slides actually for the glucose sensors. Even in the tears, we have the glucose, the sugar level, so that we can detect that level. And in presence of these cobalt oxides that can change the morphology of the affected cancer cells. These cancer therapy and for right side interaction, the DNA of another on cancer cells. So that change we can observe the sensors. Here again, these are the porous structures. You see, these are small porous structures is formed 2%, 4%, 6%. This doping of copper to the cobalt oxides. 2% is a smooth and compact. 4% is homogeneous particle size and arrangement. But at 6 atomic percent started to increase the roughness and porosity. So here, these XRD, they have done, the students have done these XRD, and these XRD results shows that the films are polycrystalline. This is not very sharp, the reflection peak. So that's why that we said this is the polycrystallines. More preferable orientation is the 311 plan. The crystallite size varies from 24 to 29 nanometer with a copper concentration from 0 to 6 atomic percent, and minimum size is 24 nanometer for 4 atomic percent copper concentrations. So these the size is varying from 24 to 29. So the minimum is 24, and that was found for 4 atomic percent here. You see the 4 atomic percent is 24, then 29, 27, 24, and 26. So this is suitable, and that we also observe from the SEM image, dislocation and texture coefficients. Second, we tested actually this 4-probe method here. These are the actually the film, and with film and without film. With film, we measure the resistivity, and then again we use the without with the solutions. One time we have taken the reading, and without solution we have taken the reading with the film, and with the solutions is also. Here in the glucose solutions and sodium hydroxides is used here just to accelerate the ionic reaction and to contact to the anode and cathode systems. There are two references we used here. Is the one is the reference is the zinc is the anode, and this the copper is the contact electrode for the anode, cathode. So these are the systems we measured here. And we see that the copper concentration we increasing from 0 to 46, and then the resistivity we measured here, the 4%. Because it's the 4% we observe, this low concentration is always the better. Because the high concentration, that is the formation of alloying and the more complex, more reactions. So this low concentration, that 4% we got the better the result. And as this is we used for sensitivity purposes, we have to calculate the rising time, response time, and recovery time is important. Rising time, what is this rising time actually? The time taken to reach the maximum, from minimum to the maximum value of the current. So this is called the rising time. What is the response time? That is the steady to reach that the value. The response time is represents the sensing of the glucose level. Until they reach the steady state, we cannot record anything. So recovery time, again, from highest value to the lowest value, to come back to from highest value to the lowest value, values of the current, that is called the recovery time. So the rising time, response time, recovery time, we measured here from the glucose sensitivity for pure, for 4% copper doped, and the 6% copper doped. Next slides we see here, this is the response time you see here, 1.16 second, 1.09 seconds, 0.97 seconds, 1.03 seconds. So what is the response time is the minimum that quickly they can respond to the uptake of the glucose, the molecule, that is the 4% here is suitable. And that also we have seen from the surface morphology that 4% is more compact and suitable for the absorptions of uptake of the glucose molecules. So the conclusion is the addition of copper as a dopant for optimization of cobalt oxide for better sensing. Copper has the good catalytic activity for oxidation in surface sites. Copper leads to greater absorption of oxygen for the detection of biocomponents. Copper can maintain the electrical resistivity as ionic radius of copper and cobalt is more similar. In most cases, the transition metals, they have the ionic size and is more or less the same. Incorporation of cobalt ions by foreign divalent metal like the copper can result in spinal structures which with enhanced catalytic activity and stability. So that is the other phenomena. But simply we can say from the resistivity values and for the response time calculation that 4% copper doped cobalt oxides, so thin films is suitable, and we found the good response time for the glucose sensations. This is maybe the last actually the results and discussion of these the copper doped manganese oxides, so thin films. Here you see these are the films we deposited here, the pure manganese oxides, and then 2%, 4%, 6% copper doped manganese oxides. Here, there's a small the particles and very fine and tuned particle is possible here. And because of that temperature, that is important part. We have to select initially which temperature is the best. Temperature is best for the complete reaction and decomposed of the samples for the formation of the films. These are the XRD here. You see the pure manganese oxides, 2%, 4%, 6% is manganese oxides here. And this paper is also published here. The Springer Nature Applied Sciences. Pure the 2%, 4%, 6% here you see here. These are the 6% here crystallite size, micro strain, and the density. Because of this the particle size also we have seen that the is better here. Iron doped manganese oxides, thin films here. The mainly iron doped manganese oxides. Here the surface morphology of pure manganese oxide thin films is made up of all the granular and agglomerated nanoparticles. And approximate size is about 15 to 30 nanometers here. But when we doped the 2% iron into the manganese oxide, then surface is more compact, relatively the first one agglomerated to 2%. But the here 3, the 4% iron doping indicates more compact and highly porous surface, and density of these nanoparticle severely degrade due to continuous increase of the iron actually effect. So the size and density of the nanoparticles started to degrade 4%, and this 6% is also here. Then finally is the 8% is also crystallite size is almost like the flower shape, the structure formation of the irregular shape. And these are the XRD is also, these are the mainly these manganese oxides is the structure is the tetragonal structures. We calculated the structures and lattice parameters, everything. 2% film intensity peak is reduced and increased, revealing that the crystallite size quality is weakened by introducing the doping. But when that 4% is iron is doped, that peak intensity is enhanced. Here is again, although these peaks are very sharp, but the crystallite size when you calculate it, then it gives the good quality crystalline size at the 4% and greatly improved than other concentrations. These are the average crystallite size we found at these 24, 22, 20, 28, 30. The 4% is the crystallite size is better than here. The lattice and dislocation density, texture coefficient. So these are all the parameters. Resistivity is also here. We calculated as the iron is doped, so the Hall effect, Hall mobility we measured, and this 4% is a concentration. This mobility and the Hall coefficient decreases with the 4% iron concentration. And because of this shortening of the mean free path of conduction carriers by scattering from the surface, and decrease of the Hall coefficient caused the local inhomogeneities in the structure due to the different size of iron and manganese may be the cause. And increase of, this is here, increase of the charge carrier concentration with increase of the iron concentration is probably due to the creation of more acceptor levels with the manganese ions, as the iron ions want to half filled, releasing an electron from the outer shell. These are the mechanisms. Again, we calculated the response time and the recovery time here for these the iron doped the manganese oxides. These are the blue and the red, green, yellow. These are the three-dimensional images of absorptions or recombinations of electrons for the glucose absorptions. So that is plotted actually. This has done due to the sigma plot 14 soft, where it was used to cross sectional views. In these three-dimensional views, the blue color represents the direct recombination of the electrons, conducting electrons. So the blue color represents the direct recombination of the conducting electrons. Green color represents the recombination of superficial electrons leading to visible emission. That's why this is the visible range. Superficial from surface that electrons is released, that is recombination. And finally, the red and violet or yellow region represents the oxidation reduction reaction. So this is happening because of that oxidation of the glucose in contact with the oxygen. There is oxidations, change of the properties, and this three-dimensional image. We can cross-sectional views of this portion. We can say because of the recombination of the conducting electrons and superficial from the surface of the electron, and that is the oxidation reduction reaction for this red color. So these are the image for you see the A, B, C, D, E means that the glucose concentration is increases 0.05, 0.1, 0.3, 0.5, 0.4. But for that 4% doped these the manganese oxides, that gives these actually the better better response of the glucose here. And here you see the cross-sectional views may be due to the oxidation of glucose on. These cross-sectional views, mainly the dark red. This is the dark red, shows the sensitivity of 4% iron doped manganese oxide at different glucose concentration. When we prepare the glucose concentration is 0.05, that is 92%. 0.1, that is 97%. 0.3, that is the 102%. Then 0.5 is 112%, 112%. And 1 mole concentration of this, the glucose concentration. So depending on the different glucose concentration for the same film at 4% iron doped manganese oxides gives the better absorptions actually. The image of oxidation of the glucose. This represents the oxidation of the glucose mainly. So these preferred that which percentage is the mainly 92% point minimum, these increases. So there is a rapid increase of that the oxidations with the increase of the glucose concentrations. So this is actually finally I will say some the summary of our work. Most of this work was done by my students from the lab. So these first of all, we use this low cost technique. This is the spray pyrolysis technique. This is completely a non-vacuum system. We don't need any vacuum. We can use even the glass substrates, plastic, paper, or even cloth as a substrate we can use. This is a high optical absorption coefficient and suitable bandgap. We can tune the bandgap by changing the surface morphology and properties and by reducing the particle size. So these could be a suitable and simple route for the synthesis of nanostructured thin films for gas sensing and optoelectronic applications. Here, the several different metal oxides systems have been used as a sensing material such as the zinc oxides, tin oxides, iron oxides, titanium dioxides, cobalt oxide, manganese oxides, thin films. And we found these materials are suitable for sensing purposes. And we tested the zinc oxide for hydrogen and we tested the cobalt oxide and manganese oxide for the glucose sensations. So these sensing properties are related to the material surface, where the molecules are absorbed and surface reaction takes place. Highly dense porous structure with clusters of the crystallites are found in above the samples and suitable for sensing purposes. It may be the gas, it may be the alcohol, it may be the humidity, it may be the glucose. So the all purposes that can be used. Surface reaction, what does what happens actually when there is a reaction takes place in the surface. So due to the absorptions of oxygen or molecules, the surface reactions change the concentration of the carrier charge concentration, and that change the depletion layer. And that due to that, the dipole moment created at the interface, and which gives the change of the electrical resistance. So the first of interaction of the molecules on the surface interface and creating a change of the depletion layer, and due to that, the development of the dipole moment at the interface, and that will also change the electrical resistance. So we succeeded in fabricating the cobalt oxide, manganese oxide, tin oxides, titanium dioxides, iron oxides for the sensing purposes and as a sensors that can be used. I would like to acknowledge my students actually. They did all of this work, and this PhD student, Dr. Mehnaz Sharmin, already completed on iron oxides, and Muslima Jahan is waiting for her defense, PhD defense, and these MPhil Raqibul Islam, Taposh Chandra Pal, Rabia Rahman, and MSc Mujibul Haq Babu, Vedant Chandra Dev, and Nurul Islam. So I gratefully acknowledge their names, and because of their hard work only, I am able to show all these work that they perform in my lab. And this is the group team in my lab. This is Mehnaz Sharmin, this is the Muslima Jahan, and this is Rabia, and this is the Tapash, and this is the Bidan, and this is Tapash, and this is the Mojibul Haq Babu. So just I mentioned, and that part, actually these are the few slides. I will show this out of our work. We have communicated in 2020, this Muslima Jahan Babu, and Muslima Jahan is also. And next is Bidan Babu, Muslima Jahan, Mujibul Babu, and these Mehnaz Sharmin, Taposh. And these are all the publications related to the oxides material we have done. And thank you very much to the audience. And again, I would like to thank Dr. Priya Murugashan for inviting me to give a lecture. And very sorry that initially I could not connect this actually with my computer. I used the MacBook. Then that is maybe sometimes, interface and connections and some things they don't support. That was my failure, but I apologize to all of you that for a few minutes, the time delay to start my presentation. And but anyway, finally, I was able to connect and to give you a presentation. And very much, yeah, Dr. Priya Murugashan, for your invitation. And please, we can talk to now in details about our research. If you have any questions, so definitely I'll try my best to answer.
Yeah.
If I can, then I'll be very happy. Okay, thank you.
Yes, sir. We are, thank you, sir. Thank you for the nice presentation. We are getting wonderful feedback from the audience, and they have given it is a very wonderful session to know about the thin films, metal oxide thin films. And here are certain questions, sir.
Yeah, please.
Will the thickness of the film be same throughout? That is the first question. I have posted it there, sir. You can see it.
Okay. Already you posted, right? Yes. What is the thickness of the film be same throughout? Yeah, that question is actually we get the on an average thickness actually. Thickness means in the whole film surface that depends on the decomposition. That the when we use the heat temperature on the hot plate and substrate, and we use a 1 by 1 centimeter square centimeter area. So that is a very good question. Thickness, there is some variation. It is true. But what we do, we take the average, but more or less same, that you can say maybe one part is 120 nanometer, the other side is maybe the 100 nanometer, more or less same, but not accurate, the same thickness over the whole film. Because of this, the deposition process is the formation of the island on the substrate. So that's why we got sometimes irregular, but more or less that we can optimize, we can make a more or less a same thickness if we can precisely control the temperature on the substrate. That is possible, and more or less the same. Again, the second question, what type of material is a lanthanum oxide, insulator or p-type or semiconductor? That is it is possible for application. That is true. Lanthanum oxide is also they are using. The suitable material for doping is also this rare earth metal, actually this material, and this is insulator. If you see that the electronic configuration on the D shell, if there is a odd number of the electron distribution, then only you can say this is the insulating characteristics. Even the material is metal, but the properties shows like the insulator, that is the large band gap. So this the transition metal is also because of the large wide band gap material. So I think if we see that the electron configuration, electronic structures, then we can decide this material may be suitable. But this material for gas sensing or the glucose sensing or biological sensing material, I did not see that any recent paper. Maybe it could be suitable. We can see it actually. Is there any other advanced technology for morphology other than field emission scanning electron microscope? Definitely, actually, what we do that if we have the TEM, tunneling electron microscope, and this mainly field emission scanning electron microscope only for the surface morphology. That surface morphology is atomic level and agglomeration, that the crystallite size that we can do. But if we go in deep, that is the tunneling electron microscope would be better than for correct interpretation. And surface morphology, normally the molecular behavior and agglomeration, formation of the crystallites that we can observe, and but better than tunneling electron microscope also. Is there any relation between particle size and sensor sensitivity? Definitely, the particle size depends on that. If you have the bulk size and the grain size is more bigger size, then you have the more resistance. But you need that the porosity. Then porosity comes within the grain size and intergranular surfaces. So this intergranular surface, if you can make the porous structures, fiber structures, and the hole or the void, so that will help to absorb the gas molecules or humidity or anything. So that purpose we need the porous structures. Particle size should be smaller. At the same time, if you have the more compact, the nanoparticle without any porous structures, that is not suitable for absorptions. For sensitivity purpose, you need the nanostructures as well. In the same time, you need the porous structures. So the more porous is more absorptions. So that we have to think about that. Uh, can you be able to measure the D and L? This experimentally that only we can calculate the actually the diameter of the grain size, that is the but the layer is the depletion layer or Debye layer, that experimentally we cannot calculate. I don't know is there any relation to calculate the depletion layer that I don't know right now, but it's a very good question. So then definitely there is a relation in between the D and L because of that the barrier formation, right? And depletion layer because of that in between the two grains, there is a two charge, electron charge, they interact. So there is a repulsive force of the same charge and they produce the resistance in contact resistance. So that is important, but maybe experimentally, I don't know right now that the calculation of the L, but D definitely we calculate from the XRD full with half maxima, the crystallite size we can calculate easily. For iron oxide, after annealed, average grain size is increased. Uh, Average grain size is increased. Actually, there is these iron oxides average grain size is increased. That depends on that you see that the thermal reaction takes place. So if you have the high temperature again, they started to the much more collisions and in presence of some other impurities and they can expand. But normally at low temperature and slow process that we can tune and we can produce the compact. But that at a high temperature, annealed after grain size is increased. For iron oxides after annealed, average grain size increased. Average grain size is increased. You see that uh, uh, mainly annealing effect. What happens actually, annealing effect? When we add the temperature, there is, you see the crystallite size and they started to separate from one to each other. So there is an expansion, thermal expansion is also there, right? The bond length is increases there. So that may be the cause that the average grain size because of that extension of that the bond length with the change of temperature with the annealing effect, that may be the cause for that the increase of the grain size also. How you know which thin film is perfect specific sensors? Yeah, that is which thin film. That is a very good question. Which thin films we need? We need that thin films which is low cost, easy to fabricate, easy to deposit, and non-toxic, and very fine thin film. If we can deposit, that materials is suitable for sensing purposes. So we have to think about the substrate, we have to think about the deposition process, we have to think about the quality of the film, we have to think about the substrate on which we will deposit the films. So these are the many, there are many parameters that we have to think about for suitable means. if 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 we want to make it cost effective, then we need that the all parameters we have to compromise. Normally the good film and the stable film, stoichiometric film, and reproducible film, and non-toxic film, and suitable around 100 to 200 nanometer size, and stoichiometric film if it is possible, then suitable for the sensor purpose. Is there any choice of substrates for different deposition techniques? Especially different deposition techniques, yes, we have limitations. Thank you, Dr. Chandrasekhar, for your question. Here you see that spray pyrolysis deposition technique, we can use the temperature up to the 500 to 600 degrees Celsius. If we use the plain glass substrate, the normal glass substrate, that stands up to the 500 or 550. But if we use the 600 or 700, but this is the open systems, you see, so there is a temperature limit, and that's why we prefer the spray pyrolysis at low temperature. Low temperature means starting from 200 to 400 or 500 degrees Celsius, and that is sufficient for making the good film and substrate. Definitely there is a good addition that the agglomerated particle, nanoparticle with the substrate. If it is the FTO, if it is the ITO, and that is the indium tin oxide, definitely there should be the good addition. Especially for the spray pyrolysis deposition technique, all these films I have shown, and that is deposited on the plain glass substrate. So we did not use that FTO. Yes, that FTO or ITO for contact or for the preparation of the solar cell, then one P-type or N-type that we have on the bottom. So that is the for contact point of view, that is okay, that is good. But for good addition also, that ITO is good, FTO is also good, because of there should be the good matching. That depends on that the phase. So normally if we can use, that is okay, but we know that the FTO and ITO is relatively very cost is very high, is a costly substrate. But for especially the spray pyrolysis system, we don't need that the high quality substrate. Even the plain glass substrates, then we have a very good adhesion and good contact and homogeneous film. We have produced, and it is easy to produce by anyone, that is the simple substrate. And again, and which domain mesoporous or microporous working is more this mesoporous or microporous working is more accurate. That is a domain is that is microporous is definitely meso and microporous definitely is more accurate, is microporous structures. If we can look at the SEM structures, that is possible definitely. Informative session. Thank you. Once if a question, if it is difficult, calcination and annealing, how should we answer? It's an informative session.
Calcination and annealing, the difference between.
Okay, just I'll see the full question between what is the difference between the cancellation and annealing. Okay, you see that the annealing you need that the only annealing you can do in inert atmosphere. You can do at oxygen atmosphere, or you can do at normal atmosphere, right? But calcination, if you need for longer time, and you need some media also, that, or even in other media also you can do it. But annealing here, we can anneal actually even in open system. Here is the film we deposited, we can anneal in open. We don't need that because the oxide films, we need the more oxygens from the environment, so it will react with the film surface, right? The oxygen will come and contact with the film surface. But calcination is normally you need some closed system, and then high temperature, very high temperature. But here annealing, we do for these thin films is low temperature for longer duration. Calcination is also you need it for longer time. So it depends on that the material. We don't need that calcination for the all material. If we want to make the magnetic or the complex the matrix, then you need the calcination, because of that high temperature. You want to remove something from that, right? But for annealing, I want to keep all the substance the remain. Only the temperature, that bonding and temperature related, they will change the properties without changing the main component to remove or to oxidized or to volatile product, without any release of that material. That we need the annealing, keeping the substance same. But calcination, for that you have to change the many phases because of high temperature. That will change the properties also. Selection process of the thin film for making a sensor. That is also selection means we need that the oxides films, and we have to test it, because these are very common, that the tin oxide, zinc oxide, titanium dioxides. Only this oxide material is coming up late 60s actually, you see. And now last 20 years, the people are searching the transition metal oxides, and because of the transparent electronics, they are looking for the transparent electronics. So transparent oxides materials are also searching. So out of that, the new materials are coming up. if we can reduce, if we can synthesize the nanomaterial, selecting then the best and the cost effective and low cost material, definitely that will be suitable for making the sensing purposes, right? So every day the new materials are coming up depending on the nature of the material, and that nature, the morphology you can change from the structural point of view, from crystallographic point of view, for morphological point of view. So that will change your optical, electrical, structural, thermal, and magnetic as well, the properties. So depending on that, the material we can select, and which material, unless we detect, we use as a sensor, we cannot say that this material particularly for these purposes. Why the grain size of zinc oxide reduced when it is dipped with the cadmium? Actually there may be the, you see that the cadmium is maybe the cross-linking process when we use that the zinc oxide with the heteroatom other than the zinc material, or that can change the cross-linking and can break the bonds. Actually these are all the fibers, long chain fiber structures, right? So the cadmium that reduced that the fibers, they break the fibers chain. So ultimately they form the small the grain size actually due to that cadmium here. The grain size mainly reduced because of the addition of cadmium, and that can rule that can the change because of the oxidation condition and coordination number that change that I already mentioned initially. What is the purpose? The reactivity is the main catalytic effect, and that the change of that the chemical behavior, and that change of that the coordination number. So many things that can influence that the addition of cadmium on the zinc oxide. So can you suggest any open wire for calculating the characteristics like XRD, FTIR, any open wire for calculating characteristics like XRD, FTIR? Actually, you see that the FTIR we use to estimate the bonding, actually the functional group, to identify the functional group only, because it is suitable for the organic molecules, right? When these are benzene, alcohol, or sulfate, phosphate, hydroxyl group, or carbonaceous material group, carbon group. So they are connected with the single bond, double bond, triple bond, the carbon atoms with the nitrogen, hydrogen, oxygen. So these are the all hydroxyl groups. Organic materials is suitable for FTIR to see that the bonding characteristics, or to calculate the functional group, to assign the bonding characteristics, right? Bonding structures and other things. But XRD, definitely we can calculate the crystal lattice and crystal structure, unit cell, lattice parameters. So this is definitely, that is the quantitative information about the crystal formation, crystal structures, unit cell structures, lattice parameters, cell volume, everything we can calculate using that XRD. But FTIR only we can assume, and that we can predict the qualitative information about the band structures, about the bonding, about the functional groups. That only we can detect actually this, the FTIR. Lecturer in physics, World University. He is my student actually. They are working, and what I have presented today, that is your work. How can you produce a gas sensor device at a low cost? That is a very good. You see there, the tin oxides, normally I tested that my sample in Japan. The tin oxides, this material is very common and very common use for the gas sensing purposes. So that we need for commercialization, that is one thing. Other in the laboratory that we can sense, but definitely that improvement for industrialization, that we need that industry collaboration with the industry. But definitely these oxides, these are mentioned, these all binary and ternary oxides materials are suitable for sensing purposes. How you choose the element for doping in the metal oxides. So that you need, that matching is important. If you have the cubic structures, then if you select the cubic, or if you have the select the ionic radius is important. It should be the comparable. Then only interstitial position or substitutional that can do it, or even the lower ionic size can go inside the lattice and can make the good the thermal, mechanical, and chemical properties. So it is always suitable, the comparable size, a little bit less ionic size is better. Then only you can take part the rule of that the doping element. Otherwise, if this is the bigger size, so that coordination and bonding phenomena will be different. So we want to intact the prime material, say as the iron oxide. Only the major prime material, mother material is zinc oxide or the iron oxides. But I want to change the zinc oxide's property by doping the other third element. So that doping should be comparable to the ionic size of the zinc, right? Or the, if it is the mother material is iron oxide, doping should be equal or less is normally preferred for having that the better properties. How many times we can use the device for sensing, and what is the lifetime of the sensors? That is only in laboratory. I cannot say that the lifetime depends on all items, is the quality of the film and device, and that depends on that the film and device. So definitely when we will go for a final the fabrication of the device, and definitely if we can use the good quality film, and then efficiency should be very high. If there is a short circuit or any contact resistance is a problem, that will damage the device. So that depends on that many factors. Presence of porosity in the synthesized sample good for gas sensing purposes. This is okay. But when we perform the calcination with those porosity vanishes, and then how gas sensitive property will increase. Yeah, that is true actually. Then this calcination, uh, but we must need that the porosity, the purpose of the absorption. So absorptions depends on that the surface morphology. And if surface is the more porous, more rough, more irregular, then only that surface can uptake the molecules, right? Either the gas molecule or the glucose molecule or the environmental or humidity or anything, the gas. So that depends on that surface. The calcination, that is okay. That because of that purity vanishes, removal of the all the byproduct impurities, you have the stable phase. But you have to create actually that porosity. Unless we can produce the porous structure, that is not suitable for the gas absorptions. The calcination is better for having the single phase or the stable phase. If we want to produce, then we go for the calcination. And ultimately by calcination, we are removing all the unwanted impurities material from the prime matrix and complex material. So that purpose, we cannot produce that the porous structures. Porous structures is always we need the thermal reactions, and then only we can produce the nanostructures with porous structures. So that is suitable for the gas sensing purposes. Here, this thank you for a wonderful presentation, sir. You have mentioned the porous film is good for the, how can I know the suitable dopant for different metal oxides for gas sensing purposes. Yeah, that is, you see here, Dr. Parveen, she asked that we are all looking why we are doping that the copper, iron, zinc, so different transition metal we are using to get the better surface morphology actually. The purpose is actually the common transition metals. If we use, those are very common, easy to buy, and low cost material like the copper, aluminum, iron. These are all the transition metal is very. But if we use the rare earth metal and poor transition metal, that is not suitable for this purpose. That's why these zinc oxide, tin oxide, titanium oxide, vanadium oxide, tungsten oxides, cobalt oxides. So these are very common material, and that we use, and all researchers are searching using this low cost transition metal. They can go directly interact with the prime material. So the selection of this material is better always by choosing that the same ionic size with the prime material first of all, and that should be equal or to less little bit is better normally for selecting the dopant element, so they can interact with the interstitial side or substitutional, or they can play important role within the matrix mother material. So that is the phenomena we are searching. We don't know that they're everything, but we are searching. So the research is the searching of uh, new material from the known material. So yeah, this is the common, we are saying that the research, what is the research? Research is the searching of the new material from the known material. So we know everything, but again, we don't know by doping. Even the co-doping is also helpful for getting the better properties. The main purpose to change the crystallites properties, surface properties, and to create the hole or void or porous, and that can only create the oxygen deficiency, and that can change only by the transition metal, because the D shell element, they're the unfilled the shell. So they can change the oxidation state. So because of that properties, we always prefer the transition metal. And which transition metal? Those metals are very easy to buy, easy to get from the market. So that is the main we are searching in our everyday work. The low cost material, low transition metal, those are available in the market. So that is the selection. But at the same time, lot of series of materials actually, you see, the transition metal group, if we use that 1 to 12, the periodic table series, that is enough that for searching the new properties and new combination also. The people are also doing that, the co-dopant element also they are doing, and getting the better result and information. So any more questions?
Okay, sir. Thank you so much, sir.
Again, actually, Dr. Priya Murugesan, I'm so sorry that initially the starting was not good, but anyway, what you can do, you can cut that portion, the initial, when you make the video that already online, but I think that portion 10 to 15 minutes, please unnecessary that portion you can just remove from the
Sure, sir.
video,
Sure.
and that will be good for the listeners. And I personally would like to thank the Chennai people. My good friends are there, and whenever I have any opportunity to visit the Chennai, that is the pilgrim place to me, and I like very much the Chennai city, the Chennai people in whole Tamil Nadu. So hope to meet you again in near future when we'll have our normal life. And definitely, I would like to thank the audience for listening, for hearing, and for joining with us this webinar lecture. And very little information uh, anyway that I have given to all of you. And this is the learning process. We are learning every day, and within our limitations, we have to do work. That is our spirit and motivation. So that's why that I have started doing that, the spray paralysis, simple technique. and low cost technique. But even then, that materials I have shown, this very good quality films is possible, because if you miss to produce, if you fail to produce the quality film, the no, don't worry that you take again second run, third run, fourth run, though the cost of material is very minimum, inexpensive. So that's why that anyone can use this low cost technique and simple technique for film deposition. Again, thank you very much. Uh, this is the end of our presentations, or any more. Still we have is the 71